Hello everyone. Today we will continue our discussion on the transformer topics. So last class we discussed together how to identify the parameters of single phase transformer, and we mentioned that it is going to be the same for three phase transformer. The only difference is the power relation that we will use. We should take care of the consideration of the power relations in terms of phase or voltage magnitudes, and power relation considering number of phases in calculations. So this is the only difference of between the calculations in three-phase and single-phase transformer parameters. Today, we'll discuss one of the topics or one of the evaluation parameters of transformer, which is voltage regulation. So what is the voltage regulation and why do we care about the voltage regulation? So this is our discussion today. So firstly, most loads connected to the secondary of the transformer are designed to operate at essentially constant volts. This is normal, guys. If we have a transformer, so we make sizing for this transformer in order to provide the load voltage requirements. And the load requirements is to have constant volts. Otherwise, this may affect the connected loads. You know, guys, we have one type of protection called under voltage protection, for instance. Okay, we use it to avoid having undervolt across loads in order to avoid higher current absorption from the loads. So every load will consume a certain amount of power for dynamic loads, like motors, for instance. If we supply this load by a lower volt, so the current would increase in order to compensate the shortage in volt in order to get the same amount of power. You know, this is for dynamic loads. For static loads, it's completely opposite. You know that power, guys, equals or proportional to VI power factor. So in case of dynamic loads, power should be constant, which means if V decreased, current will be increased. And for sure, the current increase may burn a lot of things, maybe burning the cables, maybe burning the load itself. So it's very dangerous. So we should make sizing for our transformer to provide constant output volt. However, as the current is drawn through the transformer, the load terminal volt changes because of the voltage drop in the internal impedance of the transformer. So if you imagine that we have a certain input supply of the transformer, so if this is our transformer, we have here a certain V input, and this is the output volt required, and you have some internal losses and voltage drop across the transformer. So in case of having any kind of variable loads and supplying the transformer with constant volt here, so the output volt here would be different. The output volt would be different. This is due to the load change. So due to the load changing, the voltage drop across the transformer impedance change as well. So this is, guys, load dependent now. So the load is connected here, and since this current of our load is changing, the output volt would change and the volt drop across the transformer also would change. The volt regulation is defined as the change in the magnitude of the secondary volt as the load current changes from the no load to the load condition. If this value of the volt regulation is relatively high, so this means this transformer would provide a lot of variations of the output volt. What is the solution in this case? We should find a solution for our loads or redesign our transformer in order to have lower voltage regulation. Because by the end, volt regulation is going to be a function of the impedance of the transformer. So if we couldn't make redesign for our transformer, so we have to provide a solution to keep the volt constant at the load side. How can we do that? There are a lot of techniques, like for instance, injecting some source of reactive power from the low voltage side at the load side in order to compensate the power factor and at the same time reducing the load current, and in this case the volt here would be better, or the volt drop across the transformer would be less because we reduce the inductor current. I think we covered the power factor correction before, and you observe that if we inject reactive power in case of low power factor loads, this would reduce the overall absorbed current from the source. And this leads also to reduce the volt regulation across our transformer. And this also will make our output volt is constant enough to keep our loads safe and avoid any abnormal conditions. So this is a concept why it's important to know the voltage regulation of a transformer. So again, we can solve the constant volt of the transformer by two ways, either by redesigning the transformer to have lower volt regulation or having external device to compensate the reactive power. By the way, such a device, guys, is referred to as power factor correction. This is in low voltage side, or sometimes in substations also we refer to what's called static VAR compensator. Static VAR compensator. So static VAR compensator provides reactive power in order to keep the voltage constant. So these are the solutions, and both of them are making by the end the same function, which is keeping the power factor close to unity and inject reactive power to the grid to reduce the current value and keep the voltage constant. So this is how can we keep the voltage constant in our grids. How can we calculate the voltage regulation? So as we mentioned, it's nothing but the difference between the voltage in case of no load and full load. So here we have a phasor diagram representing our transformer. Let's firstly write down the relation of our transformer and drive this phasor diagram. I'm going to do that in a separate slide right here. So you remember, guys, our equivalent circuits, assuming the approximated equivalent circuit. So we will have something like that. We have here Z equivalent. We have here V1 and V2 prime. So this is referred to the primary side. And this is the load current, which is I2 prime. So we can say here, if we apply Kirchhoff voltage law, we can say V1 equals V2 prime, which is the load current, plus I2 prime times Z equivalent, where Z equivalent equals R equivalent plus JX equivalent. If you draw the phasor diagram of this circuit and this equation, consider that V2 prime is reference. So if this is V2 prime, and most probably our loads are lagging loads, so it takes reactive power. So in this case, assume that I2 prime is lagging like that. So you know Z is R plus JX. So I times R would be in the same direction of I. So this is I times R, I2 prime times R equivalent. And you have J X equivalent times I2 prime as well. So by the end, you would have I times Z here, I2 prime. So in this case, guys, this is going to be the volt V1. In case of no load and full load, this current would be smaller or higher. So in case of no load, in this case, we can say V1 equals V2 prime. So assuming no load means here open circuit, so we don't have any current. So V1 equals V2 prime. And in case of full load, our load volt is going to be V2 prime. So if we go back now to the relation here, you will find that no load volt is V1, full load volt is V2 prime. So we can subtract V1 minus V2 prime, divide V2 prime. So this would give you the percentage voltage regulation. V1 minus V2 prime divide V2 prime. So V1 can be calculated at any V2 prime. V1 can be calculated at any V2 prime. So in this case, we will assume that V2 prime is constant, and based on that, calculate V1. So we can calculate V1 using this relation. And considering V2 prime is constant, which is the load volt. So if I have a transformer, guys, of 2200 220 volt, and I'm calculating the values referred to primary side, so I can say V2 prime is 2200. And since we assume that V2 prime is at angle 0, reference all of the time, so we can say from here V2 prime is 2200 at angle 0. And based on that, we can calculate V1 to calculate the volt regulation. Let's see an example together. So here in this example, consider the transformer in example 2.2, which we already solved in the previous class, and we identified the parameters of this transformer. We need to determine the percent volt regulation for. First case, 75% full load, 0.6 power factor lagging. 75% full load means our transformer is loaded by 3/4 of the full load. And the power factor is 0.6 lagging. How can we do that? Let's firstly draw that in another empty slide here. So now we have V2 prime and we need to get V1 at the condition of 75% loading and 0.6 lagging power factor. For sure, in order to do that, we need to know the circuit parameters. So let's get the circuit parameters from here. So we have impedance of 10.4 plus J, 31.3. So we can say, or let's firstly calculate the current. So I equals, which is I2 prime. Here it was in the primary side, so or high voltage side. So let's continue with the same notations. So I'm gonna say I L prime equals 0.75 times I rated. In order to get I rated, so 0.75 times I rated equals S rated divide V rated. So S rated of this example was 10K, so 10,000 divide our V in the high voltage side, which is 2200. So we can calculate the current here. If you do that, guys, you will get the current value, which is 3.41. 3.41 ampere. And we have Z equivalent high. Again, the values are 10.4 plus J, 31.3. 10.4 plus J, 31.3 ohms. So we can say now V1 equals V2 prime, or let's say V high equals V low prime plus I low prime times R equivalent high plus J X equivalent high. So this would be V low prime is 2200 at angle 0 plus I low prime, we got the value. So it's going to be 3.41 ampere, and the angle is, he mentioned here, 0.6 lagging power factor. So lagging means the angle is in minus sign because we said the voltage is reference at angle 0. So lagging means minus angle. So minus cosine inverse our power factor, which is 0.6. So this is now the current times our impedance, which is 10.4 plus J 31.3 ohms. If you do this calculation, you would get this value here, which is 2306 at angle 0.9. So this is V high. Now, the percent volt regulation is V high, absolute value without angles, minus V low divides V low. So 2306.9. Let's say just magnitude without mentioning any other absolute values. So 2306 minus 2200 divide 2200 and multiply times 100 and in percent. So you would get 4.86%. 4.86%. So this is the percent volt regulation of this transformer in case of that loading condition. And this is going to be the maximum. Sorry, not the maximum. Here is only 75%. So at 100% loading, this value would be different now. Okay. So this value would be higher in that magnitude, because instead of having current equal 3.41, it would be 4.55. And in this case, the voltage drop is going to be higher, which means V1 is higher and the difference is higher and the volt regulation is going to be higher. Okay. So this is not the worst case we have in this loading condition. So guys, here, this is a textbook solution. So he followed up the same what we made. So he got firstly the power factor, and the angle is minus 53.13, and he substituted in our relation we just mentioned, and he got the volt regulation. Now let's see in part B, using the same magnitude of full load current, but the power factor is leading. Power factor is leading in this calculation, guys. The only difference would be the angle here. It's not going to be minus anymore. This is leading. So if you do that, you would get volt equals 2137.9. So this means V1 in magnitude is less than V2 prime. And in this case, the volt regulation is going to be in negative sign. Here, guys, I need to discuss one important thing with you, which is, now, this is very important for power system. Now, we have, let's go to the first slide. We discussed the transformer here. Assume that this is the source before of the transformer, and here you have your load. So, is it possible to have this volt lower than this volt referred to the other side, and still transferring the power to the same direction? So the answer is yes. This is possible in AC power, not in DC power. So in DC power, all of the time, the power is transferred from the high volt to low volt, or from bus bar of higher voltage magnitude to bus bar of lower voltage magnitude. Because by the end, in case of DC, let's go to our example again. In DC, we have one more slide right here. This is very important, guys, the concept of power flow. So regarding the power flow, in DC, power flows from V1 to V2 if V1 is greater than V2. However, this is not a condition in AC. So the condition of AC is the supply has to lead the load. So the power will be transferred from V1 to V2 by controlling the power factor, by controlling the reactive power flow, not by considering the voltage magnitude only. So, for instance, in AC now, if we have, let's say now we have V1, and this is here transmission or whatever, and this is V2, and this is our load, and here is our generator. Okay, so this condition is for DC. For AC, V1 greater than V2 and reactive is flow, reactive power is flowing from V1 to V2. Or V2 is greater than V1 and reactive power is flowing from V2 to V1. Okay, guys. So if V1 leads V2 and V1 is greater than V2, so in this case, power will flow from V1 to V2. But if V1 is less than V2 and reactive power is flowing from V2 to V1, so the power can still flow from V1 to V2. So these are the conditions in case of AC, and this is the condition in case of DC. So you have to figure out this difference. Otherwise, it's going to be confusing to you. So the reactive power flow in power system is very, very important. For that, controlling the reactive power flow in AC grid is very important. Okay, so this is, guys, general information for to be like basics for power system you have to understand. Okay, now let's discuss, guys, one more evaluation parameter for the transformer, which is efficiency. For sure, guys, I do believe all of you knows about the efficiency like tickets or energy consumption tickets. You can find devices with energy consumption tickets and the different labels of A, B, C, and so on refers to how efficient is the device. So if the device internally consumes less power, so the efficiency would be higher. So the efficiency of any device is nothing but P out divide P in. So I'm going to write the other relation here, P out divide P in. And P in this case would be P out plus P losses of the device. So if P losses is very small, the efficiency is going to be very high. So because P out is load requirements, we cannot control it. But we can control P losses. Control means control during design. So during our design, we can optimize the parameters of the device in order to have the lowest possible losses. Optimize means make the device to have the required power with minimal value of losses. This means optimization. So we have in electrical power one of the techniques called optimization techniques used when we make sizing for devices. So optimization gives the optimum value or the best value that fits to increase or having the maximum possible efficiency. So this is called optimization. So this should be considered while designing any device. So this is in general, not only for transformer. Here specifically for transformer, in order to do that, we need to have lower values of resistors. But at the same time, you have some other constraints like how much inductance you should have, what is the coupling coefficient, and so on, and consider also the during design of transformer, we consider some other mechanical aspects in terms of the core frame and the window of the winding and so on. So we have so many parameters. In our class, guys, we do not discuss how to design transformer, because design transformer depends on the magnetic design using finite element methods. And again, I described this in the magnetic circuit classes. This is made using the finite element programs like multi-physics programs like ANSYS, like COMSOL, and this is considered as a graduate level course. So we do not discuss that in our class, but we just need to understand the concept. So in order to have the best efficiency, you have to minimize the losses of the transformer. So this is the efficiency. How can we make calculations for the efficiency? So the power loss of a transformer is summation of the internal losses. So if we go to the equivalent circuit of the transformer, guys, we would have two different resistors. And these resistors will consume some losses. These resistors are equivalent and are core. So we have core loss and we have copper loss. So copper loss all of the time is referring to the winding loss, which is the losses on the equivalent resistance of the windings. And core loss is the, you know, that core loss, we discussed this in the magnetic topics, is the summation of the hysteresis current loss and eddy current loss. So these are the two losses in our device. Now, the core loss can be calculated at rated volt. You remember, guys, in the previous class when we discussed the open circuit and short circuit test, we mentioned that open circuit test has to be made at rated volt. Why? Because from this test, we make identification for the core resistance. And if you have a look to the equivalent circuit, you will find that our core is connected in parallel to the supply, which means if you then make the test at rated volt, so this value would be different. So we cannot make the test at different value of supply volt. So we have to make the open circuit test at rated value. For that, we can consider the core losses here as IC square RC or V1 square divide RC. So this is the relation that we use in the approximate equivalent circuits. Okay. For the copper loss, one more thing, guys. For the transformer, we will assume that we will supply all of the time the transformer from the same V1. So we can assume that P core is constant during operation. So this is like an assumption. It's not exactly constant because you know that V1 can be changed with the current magnitude according to the volt regulation we have, because it depends on the load current and how much voltage drop we have inside the transformer. So V1 would be changed as well. However, changes in V1 can be neglected especially if the volt regulation is the regulation is good on the circuit and the impedance is minimum in our transformer. So in this case, we can consider that P core is independent of loading condition. So P core is going to be constant, whatever the loading condition we have. This is an important assumption. We use it in our calculations. Also, for the copper loss, so copper loss is load dependent because copper loss is nothing but the I square R on the resistance of our transformer. So I square is the I2 prime square, which is the load current. So it depends now on our load. So we can say now the efficiency is P out divide P core plus P copper plus P out. If we consider the P out as a function of S and power factor, so it would be S output for sure. So S times power factor divide P core plus P copper plus S output times power factor. This is efficiency in general. If you would like to get the efficiency as a function of the loading condition, so assume that we have a per unit loading of X. So per unit loading of X means X times I rated. So if I say, for instance, I'm loading the transformer by 50%, so X would be 0.5. I'm loading the transformer by 75%, like the case we had in the previous example here, 75 of full load. So in this case, I can say the value of X is 0.75. So if you would like to get a general form for the efficiency as a function of the loading condition, we can say X, which is the loading condition, times S rated value times power factor, divide P core plus, you know that this is P copper. We will come to this point now, plus X times S rated. So X times S rated times power factor is the same as P out. But why here we use that X squared P copper rated? Because P copper, we mentioned here, P copper is I square R equivalent 1. If I'm working at rated current, so this would be I rated square. If I'm working at half of rated current, so I square is going to be 0.5 square times rated current square. So we can replace P copper by X squared times P copper at rated value. Okay. One more thing. I didn't write this here. I can write this here with you now. So I can say this is equal X S rated power factor divide P core. This can be replaced by P open circuit because P core is nothing but the open circuit test power. So from the test of the parameter identification, we can use the open circuit power as P core in this numerical calculations. Plus X square times P copper rated. P copper rated means I square rated value times R equivalent, which is nothing but P short circuit, because we mentioned that short circuit test is all of the time made at rated current. So we can say X square P short circuits plus P out again, which is X times S rated times power factor. So this is another important form for the efficiency to be used based on the short circuit and open circuit test data given. Okay. Now, we need to know one important thing regarding the maximum efficiency. Before going with any derivations, you know, guys, if I have a curve like that, I can get the maximum value by using derivatives. So if I have, this is efficiency versus loading condition. So loading condition is X, which is I2 divide I2 rated. I2 or I2 prime, okay? So I2 divide I2 rated or I2 prime divide I2 prime rated. Okay, whatever the side of the transformer. So this is X, or per unit loading. So per unit loading, we care about from no load to full load, so from 0 to 1. Assume that we are working at a power factor of unity, the first curve here. What is the maximum power, sorry, the maximum efficiency of this curve? So we can get the efficiency relation and make derivative according to X. So d eta divide di2, because di2 is the main factor that affecting X, and make this relation equal 0. So this would provide the value of I2 that will make efficiency maximum. I didn't include the derivation right here, but if you do that, you will find by the end that the maximum efficiency will be occurred if P core equals to 2P copper. Or let's say it in opposite. P copper equals P core, because P core is constant. So this means the maximum efficiency will occur if I2 prime equals the value that provides copper loss equals core loss. So this is the condition to have maximum efficiency. So in this case, I can say that in order to calculate the value of X that produce maximum power, so I can say P core equals X squared P copper full load. And in this case, we can say X equals P core divide P copper full load under root 2. So this is the condition now, guys. So if you calculate this value of X, you will know the value of per unit loading that provides maximum efficiency. But take care, this is only at one curve of efficiency, which is at unity power factor. But I can say now, like another definition, we have like global and local. So global maximum efficiency will happen at unity power factor. But local maximum efficiency of this curve can be calculated. So you can get the value of X in this loading condition of 0.8. Okay, guys? So we can have like two conditions now, global and local maximum efficiency. So in general, guys, if we didn't define is it local or global, you can consider the maximum possible, which is the global one, the maximum efficiency at unity power factor. Okay, so this is the condition of maximum efficiency. Now let's solve and end with this example. So in this example here, we have 500 kVA transformer, has 2500 watts iron loss. So iron loss is, right, this is core loss, because the iron loss is or the core loss is already consumed by the iron of our core. So this is the core loss. And 7500 watt copper loss at full load. At full load means this is also P copper rated, which is the same as P short circuit. And this is also the same as P open circuit. So we have both short circuit at rated short circuit or copper at rated and open circuit. And also the power factor is 0.8 lagging. So this is the power factor we have for this loading condition right here. Firstly, we need to calculate the transformer efficiency at full load. Full load means in terms of per unit loading, so X equals 1. Then transformer efficiency at half load. So half load means X equals 0.5. So we can use our relation. We have now all parameters given. This is here S rated. So we have S rated. We have P open circuit, we have P short circuit, we have X, we have power factor. So this is a direct substitution here, guys. So S is 500K, power factor is 0.8. This is P core, this is P copper, and it's times X squared, and X equals 1. So we got this efficiency here. So the efficiency is 97.56. This is the first case. For the second case, at X equals 0.5, so 0.5 times S rated times power factor, and here the P core is going to be the same, 0.5 square copper loss plus 0.5 times 500,000 times 0.8. So this is the other efficiency at 50% of loading condition. So I'm going to make one small assignment here, or quick assignment. So this quick assignment is for the previous example. Calculate. First, the maximum efficiency at unity power factor. The maximum efficiency at the different loading conditions in the previous example. Let's have this after that one. So this is a quick assignment, guys. I need all of you to do that and submit this by before of the next class on Friday. Okay, so we'll stop at this point, and in the next session we will start in the three-phase transformer bank. Thank you so much, and have a nice evening.